Okay. We're going to be looking at hexadecimal numbers. Decimal numbers. Okay, so hexadecimal numbers can also be referred to as hex numbers. That's like a short way it might be represented and often indicated, and it's a base 16 number. Alright, so again with octal numbers, if you remember, we had a range from 0 to 7. So with 16 base 16 numbers, we've got 16 different numbers. Therefore we've got a range that's going from 0 all the way up to 15. Okay, so there's 16 different numbers over there. So this becomes now again a situation. If you look at our table, we've got 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, 16 to the power of 4, and that goes up to 16 to the power of infinity. And if we had to put the equivalent values over there, that would be 1, 16, 256, 16 to the power of 3 is 4096, and 16 to the power of 4 is 65,536. Okay, so, and yeah, I'm going over 2 columns over there just because of the large number that it is. Okay, so that is sort of the same principle we're going to be doing as we did with binary numbers, as we did with octal numbers. We're going to be looking at the bases. It's going to be 16, it's going to be to the power of 0 all the way up to the power of infinity. Okay, so the thing is with hexadecimal numbers, what we've got to take into account is the different numbers. So obviously we know that as with, let's say, your decimal number, we've got 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But we've got 16 different numbers up to the number 15. So that means we're going to have the number 10, 11, 12, 13, 14, 15. Because that's going to give us a range of numbers going from 0 to 15. Okay, so if you had to look at your decimal number, let's say you looked at the number as a decimal number of 192. Obviously, you would know that that would consist of a 1, which, well, a 1 in this column. Then you're going to have a 9 in another column, and then 2 in a column. Okay, but what should happen if you would have the number of 143,810? Okay, and we had to tell you this is now a base 16 number. Okay, so a quick question: is it? Let's write this out: 143,810. I'm going to write it out 4 times: 143,810. 143,810 and 143,810. Okay, so the question is this equal to 143,810 as we separated the different digits, or I'm going to refer to them as characters now, over there for the a base 10 number? Or is it 14, that's one number, then 3810 as being separate numbers? Or is it 1 as a separate number to 4, to a separate number to 3, to a separate number to 8, but the 10 is its own number? Or is it possibly 14 is its own number, then 3 and 8 is a separate number, and then 10 is its own number again over there? So you see that if you've got 2 digits next to each other and you have to write a number with all the digits together, it's going to be difficult to associate what is it which number is being referred to over there. And for that, essentially numbers that are 10 and larger become alphabetical letters, and that's the reason I refer to them as characters. So 10 becomes A, 11 becomes B, 12 becomes C, 13 becomes D, 14 becomes E, and 15 becomes F. Okay, so now if I had to say to you that you've got a value that is E38A, you will be able to immediately be able to say, well, you know what, I know what that means. That means that that would be the 14 representing the E, which will be a separate number to 3, which will be a separate number to 8, which will be a separate number to 10. And therefore this last scenario would be taken into account. Okay, so this is where it becomes a little bit different in terms of representation, because we've got now alphabetical letters that are going to be used, but those letters are just going to be representing values as from 10 to 15. Okay, so let's have a look how this would be applied. So again, we're going to be looking at our table. Like I mentioned, we've got 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, 16 to the power of 4, and that's equivalent to 116, 256, and 16 to the power of 3 is 4096. Can continue over there. I'm just going to leave it to that. Okay. So let's say we've got a problem that is a question you asked to convert now from hexadecimal. So now we're going to be converting from hexadecimal to decimal. Okay, and you've got to convert 29F. So 29F is the hexadecimal number, and you've got to convert it to that. So essentially what we can do is we can again place it into our table over here. So it becomes 29F, and we can say, okay, well, that is equal to 2 times 16 to the power of 2, because it's the 2's in the 16 to the power of 2 column, plus 9 times 16 to the power of 1, plus F. Now what's F? F is, if you look at the list over here, F is equal to 15. Okay, so plus 15 times 16 to the power of 0. Right, and that will be then equal to 512 plus 144 plus 15. Okay, and that will then come to 671 base 10. Let's have a look at another example. So let's say I give you the hexadecimal value of bad 1. Okay, so again what you can do is you can go and place it in your table over here. So we've got 1 over there, we've got a D over there, A and a B. Okay, that is equal to, okay, so what is a B? Well, if you look at B over here, B is equal to 11. Okay, so B would be 11. Multiply that by 16 to the power of 3. Plus, what's A? Well, look at over here, A is equal to 10. Okay, so therefore 10 multiplied by 10 to the power, 16 to the power of 2. Plus D, what's D equal to? D is equal to 13. So 13 multiplied by 16 to the power of 1. Plus 1 over there. So 1 times 16 to the power of 0. Okay, that would be equal to 45056 plus 2560. 13 times 16 is equal to 208 plus 1, and that will be equal to 47825. Okay, now if you have a look at this, you will realize that writing out in hexadecimal of certain value, such as BAD1, would be easier to represent, or less typing is required compared to the number of 47,825. And that's where hexadecimal numbers and octal numbers also becomes very useful, especially when you're doing programming. It reduces the number of characters that have to be typed. Now you might ask yourself, oh, what difference does it make to type one extra character? It might in this case not be, so much more typing that you would require, but it still would mean that you need to do quite a bit of typing. So it's something that, especially if you've got long programs to do, and you've got a lot of typing that's needed, and you've got to type the same number a few times, it becomes very useful to be able to have a look at this and take it into account. Okay, so now that we've looked at that, let's have a look at converting decimal numbers to hexadecimal numbers. Okay, now again, the same scenario we're going to be doing as we did for binary, as we did for octal number systems. We're going to be doing the same procedures. So again, I've got my table over here. I've got 16 to the power of 0, 16 to the power of 1, 16 to the power of 2, 16 to the power of 3, 16 to the power of 4. Okay, and the equivalent value of that is 1, 16, 256, 4096, and 65,536. Okay. Right. So again, let's look at an example. So we've got the number 5923, and that's a decimal number, and now you've got to convert that to hexadecimal. Okay, so the first thing we're going to be doing is we've got the number 5923, and we're going to say, okay, well, that's 65,536 going to 5,923. No, it doesn't. So we place a 0 over there. That's 4,096 going to 5,923. Yes, it does. How many times does it go in there? It goes in once. Okay. So we subtract 1 times 16 to the power of 3. And we're left with a value of 1827. Okay, now we go to the next column. Does 16 to the power of 2, or otherwise 256, go into the number 1827? Well, yes, it does. And how many times does it go in there? Well, it goes in 7 times. Okay. So 1827 minus 7 times, so it goes in 7 times. 7 times 16 to the power of 2. And that leaves us with a value of 35. Okay, so now we go to the next column. Does 16 to the power of 1 go into 35? Yes, it does. How many times does it go in? It goes in twice. Okay, so we go and say 35, subtract 2 times 16 to the power of 1, and that leaves us with an answer of 3. Okay, so now 3 is our next value we're looking at. Does 1 go into 3? Yes, it does. How many times does it go in? It goes in 3 times. So it's 3 minus 3 multiplied by 16 to the power of 0 is equal to 0. Okay, so now we get to a value of 0. So we've got 95% certainty that that value, or that calculation, is correct. Okay, so therefore 5923 base 10 is equal to 1 times 16 to the power of 3 plus 7 times 16 to the power of 2 plus 2 times 16 to the power of 1 plus 3 times 16 to the power of 0, and that's equal to 1723 base 16. Okay, let's have a look at another example. So let's say we're looking at the number 3976. It's a base 10 number, and we need to convert that to a hexadecimal number. Okay, so 3976. and again I'm going to be using exactly the same table over here. So does let's have a look. Does 4096 go into 3676? No, it doesn't, so we can place a 0 over there. Does 256 go into 3976? Yes, it does. How many times does it go in? If we do the calculation, you'll see it goes in 15 times. Okay, so we subtract 15 multiplied by 16 times to 16 to the power of 2. Okay, and if we subtract that, we get left with 136. Okay, so 136 is our next value we're looking at. Does 16 go into 136? Yes, it does. How many times? It goes in 8 times. Okay, so minus 8 times 16 to the power of 1. And if we do that calculation, we see that we're left with 8. Okay, so now 8 is our next value that we're looking at. Does 1 or 16 to the power of 0 go into 8? Yes, it does. How many times? It goes in 8 times. Okay, so 8 minus 8 times 16 to the power of 0 is equal to 0. So we get the final answer of 0, which means we've got a 95% chance that our answer is correct. Okay, so therefore 3976 base 10 is equal to 15 times 16 squared plus 8 times 16 to the power of 1 plus 8 times 16 to the power of 0, and that gives us an answer of, now we've got a number 15 over there. We need to put that into the correlating alphabetical letter. And if you remember, if we go have a look at this, these numbers we did over here and that we quickly just tabulated, you would remember that 15 is an F. Okay, so that is equal to F 8 base 16. Okay, so essentially we're using the same principles as we did for binary numbers, as we did for octal numbers. The only difference over here is that we are actually going to be looking at replacing numbers that are larger than 9, and we're going to replace them with alphabetical letters. So that will be all the numbers from 10 to 15 will be replaced by letters from A to F in the alphabet. Okay, so now that we've done that, let's have a look at hexadecimal addition. Okay, so again, we're going to be doing the same principles as we did for octal numbers. We're going to be doing for hexadecimal. So let's say, for example, we've got the question of BAD 1, and we're going to be adding to that DAD. Okay, so keep in mind, always it's time to keep the different characters underneath each other in some order so that you don't mix them up. Okay, so let's have a look. D plus 1 is equal to, well, first thing we've got to look at, what is D? Okay, so again, I'm going to be looking at this table that we had to look at. I'm going to actually fold this up just to make it a little bit more easier and compact to refer to. Okay, so D is equal to 13. Okay, so 13 plus 1 is equal to 14. Okay, so I'm going to place a little 14 over there underneath it. Okay, is 14 less than or larger, or let's put it this way, is 14 larger than 16? No, it's not. So there's no carrying over that we need to do over there. But 14 is equal to E. So we need to replace that with an E. Okay, let's go to the next column. D plus A. So D is equal to 13. A is equal to 10. So D plus A is equal to 23. Okay, so we go and we place a small 23 over there. Okay, so does 16 go into 23? Yes, it does. How many times does it go in? It goes in once. So we need to carry over a 1 over there. What would be the remainder once we've subtracted 16 from 23, what would be equal to 7. Okay, so therefore we go and we place a 7 over here. Now we go to the next column. What is 1 plus a plus d? Okay, well, firstly d is equal to 13, a is equal to 10, so 13 plus 10 is equal to 23, plus that 1, so it's 24. Okay, so we can place a 24 over here. You don't need to write these numbers over here. You can write the actual number over there straight if you want to. Let's just to sort of show you what you keep in your mind. Okay, so 24, does 16 go into 24? Yes, it does. How many times is it going to? It goes in ones. Okay, so we need to carry over 1 over there. What's the remainder if we had to subtract 16 from 24? Well, it will be 8. So we place an 8 over there. Alright, now we go to the next column. B plus 1. So B is equal to an 11. Okay, so 11 plus 1 is 12. So we can place a 12 over there. What's 12? 12 is less than 16, so we don't even have to worry about carrying over. What is the value of 12? 12 is a C. So we place a C over there. Okay, and so therefore that is our answer. Again, just follow the steps as you would have done for normal decimal number addition, as you would have done for binary number addition, as well as for octal number addition. Follow the same principles, and we're essentially doing the same thing as we for hexadecimal number addition. Okay, let's have a look at another example. So I'm going to give you 3 numbers now. So let's say we're looking at 7, 4, 9F plus 3A 5, 4 plus 6, 4, 9, 5. Okay, so you've got to add those 3 numbers together. They're all hexadecimal numbers, and you've got to add them together. Okay, so let's go again through it. So F is equal to 15. 15 plus 4 plus 5, so that would be equal to 15 plus 9. Okay, so that's equal to 24. So we can place a small 24 over here. Okay, now that we've done that, how many times does 16 go into 24? It goes in 1, so we therefore need to carry over that 1. And if we look at the remainder, once 16 has gone into 24, that would be a remainder of 8. Okay, so that becomes an 8. Okay, now we've got 1 plus 9 plus 5 plus 9. Okay, so that would be equal to 18 plus 5 is equal to 23, 24. Okay, so again we've got 24. So how many times does 16 go into 24? It goes in 1, so therefore we carry that 1 over there. And what would be the remainder? That would be again 8. Okay, let's go to the next column. 1 plus 4 plus 8 plus 4. Okay, so A is equal to 10. So 10 plus 4 plus 4 is 18, plus 1 is 19. So we can place a small 19 over there. Okay, so what is, how many times is 16 going to 19? It goes in ones, so therefore we carry over 1. And if we had to subtract 16 from 19, the remainder would be 3. So we place a 3 over here. Now we go to the next column. 1 plus 7 plus 3 plus 6. Okay, so 7 plus 3 is 10, plus 6 is 16, plus 1 is 17. Okay, so we can place a small 17 over there. How many times does 16 go into 17? It goes in ones, so therefore we need to carry a 1. And the remainder will be equal to 1. So we can place a 1 over there. Okay, and then we've got 1 plus 0 plus 0 plus 0. So that comes down and is equal to 1. So that's our final answer. Yeah, so as you can see, with hexadecimal numbers, the same methodology applies as we've done with the other number systems. You just have to follow the same principle for each of those different number systems, and you'll be able to do the calculations accordingly. Again, as I mentioned before in the binary number systems, there might be other ways of doing it, but I'm trying to let you think of ways that the computer would be actually doing the calculation. because using these similar principles and methodologies that I've been showing you over here, when it comes to programming and having to do a base 32 number, for example, when you have to do that conversion from, let's say, decimal to base 32, or even from a base 32 to a decimal number, the same principle will apply and the same procedures can be followed, which just makes it easier to be able to put it into a programming language code.